section slide, and we will move over to the actual next section. And what I want to point out now is that we've shown you a lot of different types of things. We've shown you integers, we've shown you floats, we've shown you booleans, we've shown you strings, we've shown you a bunch of functions, prints, loops, whiles, fors. We've showed you tuples, we've showed you lists, we've showed you sets, and we've shown you dictionaries. So for a little bit here, we're going to take a bit of a break, and we're going to start talking about algorithms. Okay, and we're going to kind of focus in this next two classes in particular on two types of algorithms that are very important to computer science. The first one is searching, where you try to go through and search, or go through a list and find something in the list. And the second one is the problem of sorting. And we want to look at these from a couple of different standpoints. The first thing we want to look at is we want to separate this concept of algorithm from implementation. So an algorithm is a precise description of the steps necessary to solve a computing problem. And you don't see this saying in the Python language or in the C language or in the Java language. This is essentially language agnostic. This should be a description that can be understood and implemented in a variety of different ways. But it should be precise, which is kind of at odds, right? We write computer languages because computer languages are precise and the computer can understand them. But the way we get around this is we use something called gradual refinement. We start off with an English description. Maybe we throw in some math on it, and we kind of walk ourselves through how to get from point A to point B. The exercise that we often ask students, not new students of computer science, to do is write an algorithm, for example, and make a peanut butter and jelly sandwich. And what we do then is we gradually make the sentences more and more detailed. We do a couple of iterations on this till we get down to the end of where we can actually implement it in a computing language. And I want to walk you through that on at least one or two examples for what we're seeing today going forward. And that's the algorithm part. And when we take that algorithm and we translate it into a computer language for the computer, or into a language for the computer to run, that's when we've written a program. So an algorithm are the steps, and the program is the concrete realization of those steps in a specific language on for a specific computer. I'm going to go a step farther than that. This says often there are many different algorithms that can solve a problem. I'm going to say there's always at least a couple of ways to solve a problem. And often there are multiple good ways to solve a problem. And the way these things differ are going to be in ease of understanding, ease of implementation, and efficiency. So what does this mean? Well, we're going to get into analyzing our solutions. We're going to analyze our solutions both mathematically in terms of order notation and experimentally in terms of how long they take to run. And one of the things we want to look at is this efficiency. In general, in computer science, we don't care as much about how long something takes to run on a specific set of input. What we care about most is how fast it gets bad. So, an order of n squared algorithm, we've looked at nested for loops, right? And I've told you, and we've kind of demonstrated that those algorithms, if you have two for loops or two while loops even, that iterate over the same list or substantial portions of the same list, what you'll find out is that that's an order of n squared algorithm, and it gets slow fast, and that's why we need dictionaries and sets to look at things, for example, like the IMDb database with 260,000 available entries. So figuring out how fast things get bad is part of this analysis of the solutions. Order of n squared is a mathematical analysis, right? It says that for two nested for loops with specific endpoint conditions, you can expect that as you double the size of the input, you will quadruple the time required to run. In the general sense, that's not an exact algorithm. There's a lot of constants that we just throw out and omit, but in a general sense, that's what our analysis is. And if we're correct, then we should be able to see this by taking experimental timings and varying the length of the input and seeing that, in fact, as we change the input size, the size of the problem actually gets bigger. So efficiency is one of the ways that these algorithms are going to differ. Some algorithms are going to be more efficient than others on the same type of data or the same set of data or as data gets big. There's two other aspects, though, right? Ease of understanding and ease of implementation. If you're going to do something once and you have a really quick way to implement it, but it's going to take 10 minutes to run as opposed to 2 minutes, well, the difference in an hour-long solution, something that takes you an hour to write, and something that you can write in 10 minutes is 50 minutes. That's far bigger of a savings in time than worrying about the efficiency of the algorithm itself. Right? If it's going to take 20 hours, well, then you're in a different case. But if you're running something short or short-ish, and the time running is not your major concern, then certainly ease of implementation is probably a lot more important. And this also feeds into ease of testing, right? If it's an easy algorithm to implement, it's often much easier to test and debug, which means that it's more likely to run correctly for more cases. So, we have to trade off this order of n squared algorithm for small inputs that we can put together really fast against maybe a more efficient algorithm that's harder to implement and harder to test. And then there's the third aspect as well, and that's the ease of understanding. So, for example, if I'm in this class and I'm trying to teach you a certain concept, the ease of understanding, if I throw up code that's overly complex just to demonstrate how much Python I know, that's not really all that useful to you because you need to understand what's going on, and understanding those internals is actually what the purpose of me giving you code is. So there's at least three aspects to evaluating an algorithm, and which algorithm we choose has to weigh these three considerations. Certainly if we have the simplest algorithm to understand, that's also the simplest to implement and runs the most efficiently, then we're probably pretty likely to choose that one for almost all cases, right? Unless we're trying to explain something specific. All right, so that's kind of the general of what we want to talk about today. And the way we're going to apply it is we're going to apply it to finding the two smallest values in a list, right? And we're going to kind of stay away from requiring too much in our system, except we're going to have a list and we're going to have to be able to compare them with a less than operation. So we're going to really only use the less than or possibly the less than or equals operation, depending on what we're going to actually try to find. And we want to find the two values in the list, the two smallest values in the list, and their indices in the list. I'm going to rephrase this a little bit. If we have the indices and we haven't messed up the list, well, then we're actually going to be able to find the smallest values just by knowing where their indices are. So the indices are in some sense a little more important to get correct. But you get the idea. They both kind of work. So before we get started, let's talk about a few other things. This sounds like a really simple problem, right? Simple, well understood. But even in problems like this, you start getting into some nuances. So one of the things we want to look at is if we have, and I'm going to move over to my handy-dandy whiteboard, I think, for a little bit. Let's turn off my background lights. All right. So we have to think about a couple of things. And the first is, well, we've already said we want both the indices and the values, but do we care about them right away, or can we just derive the values from the indices? So we'll say 1, indices and values. 2, do we need to preserve the original list? right? Does that need to be part of our algorithm, preservation of the original list? 3, does the list have duplicates, or is the list allowed to have duplicates? And if it does, what do we do when there are? Right, so for example, if we have our list L and we have 0, 7, 0, 9, 1, 3, 0, right? And we want the two smallest values. Do we want this and this? Or do we want this and this? Right? Do we want to skip the same value twice, or do we want to find the same value twice? Doesn't matter. Do we want, we're asking for indices. Do we want this and this? If we want to find the absolute smallest, do we want these two? Or do we want these two? Or do we want these two? Or doesn't it matter? Right, so these are all questions that have to go into things that we should be thinking about when we're actually thinking about designing our algorithm. I'm going to make this simple. We're not going to worry about duplicates. We're going to assume that the list has no duplicates. The reason for that will become obvious in just a few minutes. And we're going to assume that, well, if there are duplicates, we want this and this, right? We're going to assume we need to preserve the original list. I just think that's a nice thing. I hate to go into a function and because of aliasing lose my original list. But those are kind of how we're going to treat this. But there are probably more questions that I haven't hit. We should think about those as well as we kind of go along. But we'll go through and we'll brainstorm a couple of sessions, although given we are online and given that I am now doing this by myself, we're not going to actually do a lot of brainstorming. But let me outline a couple of approaches. Okay, so for approach 1, and let's do this in two phases. I'll write out 2 levels of the algorithm. We're going to make a copy of the list. Well, we don't even have to do that yet. We're going to walk through the list. And find the index of the smallest element. Remove that element. So we'll just say walk through a copy of the list and find the index of the smallest element. Remove that element from the copy. Walk through the copy again and find a new smallest element. Find the index of a new smallest element. Fix the second index based on the original list. Return both indices. Okay, so that's one way to do this, right? We just walk through the list 2 times. The first time we find the original, the absolute smallest value in the list. Once we've done that, we remove that one from consideration, and we walk through again, and we find, again, a smallest element in the list. And those 2 elements, and then the second one, because, let's say we had the smallest element was at position 0, and the second smallest element was at position 1. After we remove this, right, the new list is going to be, so this would be at index 0, and this would be at index 0. But in the original list, this would be at index 1. So we want to return 0, 1, not 0, 0. Right, so we have to do this little step here to fix it up, afterwards to take care of this situation. And we can iterate on this, right? I said we're going to iterate on it. Given a list L1, or given a list L, make a copy L1. Index sub 0 equals 0. Well, we could just say start by making L1 sub 0 the smallest element. Iterate through the list, iterate through L1. And for each element, if that element is smaller than smallest, make this the new smallest element, right? We can put this out here as an if, right? We're starting to look a little bit more like code. Remove the smallest element from L1, and then we'll just redo this, right? Do it again on the modified list, and then at the bottom of that, fix the second index if necessary, and then return the indices. Okay, so this is a little bit more refined. And we can actually take this and we can write a program based on it. So let's go, now that we've done this, let's go back and we will look at some code. I'm going to grab this right from Code written in class. Okay, and you'll see a lot of different implementations here. If you go to the code written in class, you'll see a couple of different implementations. I'm going to pop this in, and I'm going to kill the two examples we have here. And I think what I'm going to do is I'm also going to comment out this line right here, because we're going to take another instance to do the index 2 values. And, you know, so we'll put a little pass in here so we don't execute that. And we can, okay. All right. Or we'll just return -1, -1. Right, and we can do that here as well. While we write this. Just so we can get a little test in here. Okay, and if we run these, we see we're going to ask for a number of I guess if I do that, I don't need to comment this out. What we're going to do is we're going to ask for a number of values, and this is going to allow us to do an analytical, or I'm sorry, an experimental timing of the case. And what we'll do is we just go through, we generate a list. You can see why I'm not worried about duplicates. We're just generating the numbers from 0 up until whatever number we put in -1, and then we're just going to shuffle them up just like I did earlier, so that we get a random order. And then we're going to time our two implementations. All right, so let's just implement what we had here. And I'm going to cheat a little bit. I did this the first time through, so I'm going to kind of just grab some code and pop it in there for us, just to get us started. So we have a comment block. This should be filled out better. You guys should always be filling that out better. But the first thing we said was given a list L, and I'm going to call this L because I prefer L, but given a list L, and because the previous code was written in terms of L, right? We're first going to make a copy, and now we know we're going to have two indices, so we're going to keep those in a list. We start by assuming that our smallest value is in the first element. So our first index, the index of the current smallest value, is going to be 0, and the current smallest value is going to be L sub 0, right? And now we're going to walk through our list L1, just like we said we would, and we're going to look at each element in the list and compare it to our current smallest element. And then if this is smaller, then we found a new candidate for the smallest element, so we update our indices to point to the new index. And we update our smallest value, so we're now looking for an even smaller value than we were the previous time. And when we're done, right, we got to return these. So this is the first pass through, and we'll just return indices sub 0, right? That's where we're keeping our smallest value, and we'll return -1 just for now. And if we run this, what we should find out, hopefully, is that unindent does not match any indentation level. What does that mean? That means copying is a dangerous operation. All right. Right, and we can test, let's say, 1,000 elements. Right, and we're going to get item 13 is going to be what we think is the smallest in our main code. Our array, our list is values. So if we look at values sub 13, hopefully that'll be a 0, and it is. Right, so that's just the first part of this. Now the second part of this says remove that value from the list. So again, we're assuming that there are no duplicates. So this becomes pretty easy. We can just do L1. Remember, we don't want to mess with L2. We can just do L1.remove. and we want to remove the current smallest. Right, so after we find the current smallest the first time, we'll remove the current smallest. Now we have a list without that current smallest, and all we have to do is go through again and redo this. Right, now we have to walk through the list again. This time we're generating another index, so we will just fix this up. We'll append this time. Well, we're still going to append, right? We're going to start at the 0 of the new list. The current smallest is, again, this time it's going to be L1 sub 0, right? We could actually make this L1 sub 0 if we wanted as well. And now we'll walk through it again. If we find a smaller one, we update it. This time the index we're updating is at indices 0 or at indices 1. And other than that, it all looks about right. And we now return indices sub 1, right? So this is a pretty simple loop. Let's kind of take a look at what we think this might cost. Well, to do a copy, we have to take every element in L and copy it over to L1. So if L has n things in it, this will take order of n time, right? And we write this as order of n, right? So that's order of n time. This is constant time. This is constant time appending to the end of a list. If you know the end of the list is constant time, this is constant time. Okay, this loop. We're going to go through this loop n times. And each time through, we're going to do constant time, constant time, constant time. So all of these statements, there's no loops here. These all take constant time. So this loop is going to be executed n times. So that means n times a constant is still order of n time. Okay, so far we have an order of n plus an order of n. Remove. Well, this could take, believe it or not, this could take order of n time. Right? Because to remove a value, you have to search through the list to find that value. And then you have to move everybody else down one. So you're walking through the entire list from the front to the end. So if the list has n things in it, this is order of n time. Again, this can be constant time, appending at the end of a list. Constant time. Again, we're now in the same loop as before. Nothing's changed, so this is still order of n. And yeah, and now we just do our return. So overall, this is order of n plus order of n plus order of n plus order of n plus order of a whole bunch of constants. So when you do an order notation, you throw away any multipliers, right? So we throw away the 4, and you throw away any low order terms. So order of n is the highest term we've encountered. So this is an order of n algorithm. All right, and we can run this, and this had better work. And we can do it for 1,000 items. And it gives us 697 and 93. Now remember, we're using a random process, so let's see what... oh, we forgot one part of this. The part we forgot is we have to fix up indices sub 1, right? Because it could be wrong now. So we'll just say indices sub 1 equals L dot index of current smallest. So this is the index of the second smallest element in the new or in the original list. And you can see that for this one, it actually didn't make any difference. But it will if this number is to the right of this number in the list, then it will actually make a difference, which is why when I saw that, it caught my mind. So let's do it again. We'll do 1,000 again. 671, 285. I want to get one where it's on the other side. We're getting closer. The last time I did this, it was always on the other side, and now it's never on the other side. Come on. There we go. Okay, so now we have the bigger number in the second smallest. So now we can go values sub 745, and that should be a 0, and values sub 885, that should be a 1, and now we know that this is actually working correctly for both sets, assuming again that we don't have duplicates. Duplicates can still mess this up. All right, so that's one algorithm. Let's return to our whiteboard again, and let's think of another algorithm. Well,